And the first part of the buffer management is this, determining how much space being allocated to the buffer. Yeah, the documentation says this, the buffer space should equal to the typical round trip time multiplying the capacity. Yeah, the intuition behind this is this. It has something to do with how TCP does the condition control. You see, in TCP, data being sent, X coming back. After receiving duplicate X or waiting for timeout, then the source will discover there's a packet loss, there's a condition, and therefore slow down. Right? So router in the middle there, okay, is thinking, well, I'll need to buffer the packets long enough before the sources know they need to slow down. Right? And that is at least one round trip time. And during this amount of time, there could be this much packet or this much data going through the link here. So that's why RTT multiplying the capacity here. In this example, we have the round trip time 250 milliseconds and the capacity being 10 gigabits. These are very typical values, but you see also the amount of memory requirement pretty high, 2.5 gigabits. So not exactly practical. So some of the recent study actually discovered this. If all these flows going through the routers are TCP flows, okay, and if there are n of them, we could actually reduce the buffer requirement to this amount. Still, RTT multiplying C at the top, but we can actually divide it by a certain factor. The more TCP flows there are, the more we could reduce the buffer space requirement. Okay. So n here are TCP flows, n flows here are n TCP flows. The reason for this is twofold. One being, hey, TCP at the beginning is doing slow start, starting from window size 1. The sending rate is very, very slow. Okay? And there are a lot of data we send over the internet being very, very small. And so we use a very slow rate to send small data. Okay, so most of these TCP flows run in the low rate. Okay, so we are actually not using the entire C capacity. Second is this. Even though we are in the steady state, okay, these window sizes are all pushing and dropping, pushing and dropping. Okay. Chances also high that we are not using the full capacity as well. Okay, so still also low, but not as low. Okay, in the slow start state, sending rate really low. Even in the congestion avoidance rate, it's actually lower than the capacity as well. Okay, so that's why we come up with the factor here. The second component in the buffer management is this, the dropping policy or the discard policy. So this is needed when packet arrives to a full queue, right? So either the arriving packet needs to be dropped or one of the packets in the queue needs to be dropped. Okay, so generally, pick the next packet to discard. Okay. The most common policy is this, tail drop. So this is essentially just to drop the packet that is coming in the last, okay? Because usually those who arrive early are given priority. But you could actually change that, okay? Assign priority to the packets. Some of the packets might be less important, right? So we could classify them to lower priority. When a packet comes in with a higher priority, then we drop one with a lower priority. Third, random. Of course, one could pick randomly from the queue a packet being discarded, right? The last component is this. How do we debuffer? Okay. Which packet do we choose to transmit next? Okay, so the next packet to send on the link. This is also called the scheduling policy. Typically, we do this FIFO. Okay, first in, first out. So essentially, based on the packet, based on the order the packet arrives, we take one out at a time. But one can also do this, the class-based scheduling. Okay. The way to do it is to divide the packets also based on the priority or based on the classes. Okay? And so we could assign a specific class being higher priority versus others. Or we could have them rotating turns, taking one packet from each class at a time. And we can actually allow multiple packets coming from one class at a time, and so that there are more packets coming out from a particular class. It's sort of a combination. So weighted fair queuing here, WFQ, is a combination of the priority and round robin. Let's go into each one of these a little bit more. So priority-based scheduling. So we send always the highest priority packet out. Okay, so when there are multiple classes, okay, with different priorities, so we send out the one always with the higher priority. If there are no packets existing, then we take whatever we have. Right? So here's an example. Packet arriving, some being red and some being green. Green packets are the one with the lower priority, while the red ones are the one with the higher priority. Okay. So the way it works is going to follow this timeline here. So a packet is arriving at this particular time. Okay. And so there'll be some time it takes for the packet to be served. And then after they finish serving, packet exit. So yeah, let's say packet 1 arrives here. All right, so right there, packet number 1 being served, and it's going to take some time here. Okay. At this point, packet 1 will exit, but there could be other packet arriving while we're serving packet 1. So 2 and 3 arrives here. But 2 is carrying a lower priority, while 3 here carrying a higher priority. So in priority scheduling, which of these two, 2 versus 3, will be scheduled next here? Always the one with the higher priority, which means 3 here. Right? And then next 2. Now, while we serve packet 2, if packet 4 arrives, yeah, right after packet 2 exit, we enter and serve 4, and so on and so forth. Now, if we do round robin, okay, the rotation-based, class-based queuing, we do have multiple classes, but we do the cyclical scan, okay, of different class queues and send one at a time. So the same pattern, 1, 2, 3, 4, 5 packet arriving at these point in time. Okay. But this time, okay, the second packet is higher priority, third packet lower priority. So which one do we send next? We actually send packet 3 because it belongs to the other class, not necessarily lower class, but the other class. We have to rotate. Therefore, after red packet is served, we serve the green packet. Now, because the next rotation is red packet again, so we take packet 2. Okay. Now, the next one should be green again because there's no green packet at all, so we serve packet 4, and so on and so forth. Last is the combination of priority and round robin, so weighted fair queuing here. Okay, so this is a generalized round robin, and it's almost like having some level of priority here. You assign weights to different queue. So way number 1, way number 2, and way number 3 here. Okay, so in one round, we could draw 2 packets out of the red queue, and 1 packet out of the green queue, and 3 packets out of the blue queue. Okay. In the second round, 2 more, 1 more, and 3 more, but because there's only 1 left, so we just get 1 more out. So this is weighted fair queuing.